An autonomous differential equation is an equation of the form dy dt equals f of y for some function y. Let's think of t as indicating time, then dy dt is the instantaneous rate of change of y as a function of t. This equation says that the rate of change dy dt is given by some rule. The rule says that if the current value is y, then the rate of change is f of y. The equation is called a differential equation because it involves the derivative dy dt. It's called autonomous because the rule doesn't care explicitly about time. It's just a function of y, not of t. Given an autonomous differential equation, we'll often want to solve it, which means find a function y of t whose derivative dy dt at all times t is always equal to f of the function itself, f of y. Let's look at a simple example. Let's make f of y be a simple linear function, 2y. So the autonomous differential equation is dy dt equals 2y. We could also write the differential equation as dy dt of t, as the derivative is a function of t, equals 2 times y of t, showing the explicit dependence of y and its derivative on t. This is the same thing, but usually we won't write out the explicit dependence on t and just say dy dt equals 2y as it's shorter. You just have to remember that y in this context is a function of t because we're taking the derivative dy dt. This t right here is the only indication we're talking about a function of t if we write the differential equation in this form. This equation is a linear differential equation, one of the simplest types. How can we solve this equation? That is, how do we find a function y of t that, if we differentiate, we get the function y of t back only multiplied by 2? We have three main methods. One class of methods are the numerical methods. In numerical methods, we approximate the continuous change of the differential equation with discrete jumps in time. By doing this, we get a formula for evolving from one time step to the next, like a discrete dynamical system. We can then use a computer to calculate this approximation to the solution. A second class of methods are the graphical methods. We can use a plot of the graph of f of y to determine the behavior of y of t. The third class of methods, analytic methods, involve using mathematics to find a function that satisfies the differential equation. These analytic methods can be quite complicated, but in the remainder of this video, we'll use a simple analytic method to solve our linear differential equation. To solve our linear autonomous differential equation, dy dt equals 2y, we'll use an important analytic method, which is called guess and check. Guess and check is a perfectly valid method because if you can find any function that satisfies the equation, you've found a solution. It doesn't matter what method you use to find the function, as long as you can show it is a solution, you've accomplished the task. The way to guess is to use your knowledge and intuition about derivatives to find a function whose derivative behaves in the required way. Here we want to find a function where, if we take its derivative, we get the function back, only multiplied by 2. Let's forget about the factor of 2 for a moment. Do you know any function that is its own derivative? The exponential function fits the bill. Remember that d dt of e to the t, the derivative of the exponential function, is the function itself. So, if y of t equals e to the t, then dy dt is just e to the t, or y of t itself. That's pretty close to the right behavior. We're just missing the factor of 2. We want the derivative to bring down a factor of 2. To find the factor of 2, let's think about the chain rule. The chain rule says that the derivative of the composition f of g of t gives the derivative of f times the derivative of g. Since here we want the derivative to be multiplied by a factor of 2, we want to find a g prime that is equal to 2. So if we make g of t equal 2t, this implies that the derivative, g prime of t, is 2. So if f is the exponential function and g is 2t, we should get what we want. Let's try it. Let's let y of t equal e to the 2t, then dy dt is 2 e to the 2t, using the chain rule. Well, this is exactly 2 times the function y of t that we started with, because it's 2 times e to the 2t. And that's exactly what we're looking for. The function y of t equals e to the 2t solves the differential equation. Our guess and check method worked. We used our knowledge about the derivative of the exponential function and the chain rule to guess a form for our function y of t, and then we plugged it into the differential equation to check. Here was the check part. Our guess and check method found a solution. We found a solution okay, but is y of t equals e to the 2t the only solution? What if we multiplied y by 3? We know that if we multiply a function by a constant number, that number just comes out of the derivative. Let's see if the function y of t equals 3 e to the 2t also works. For that value of y, dy dt is equal to 6 e to the 2t by the chain rule. Well, this is 2 times 3 e to the 2t, which is 2 times our new y. So the function y of t equals 3 to the 2t also works. It also satisfies the differential equation, dy dt equals 2y. In fact, so does 5 e to the 2t. If y of t equals 5 e to the 2t, dy dt is also 2 times y, or 2.3 times e to the 2t. Or, in general, any number c times e to the 2t. As long as c is just a number, c times e to the 2t will satisfy the differential equation. Y of t equals c e to the 2t satisfies the differential equation, dy dt equals 2y. The constant number c just comes out of the derivative. It turns out all solutions are of this form. All solutions to dy dt equals 2y are some constant number times e to the 2t. We call this y of t the general solution to the differential equation.